Today I want to look at a particular algorithm for compression. So before we do that, let's make some test cases. And we're going to use Python. Something went wrong there, but I think we are good. Let's actually put it down here. Okay, so how should we make these tests? Let's start by trying to get NumPy, and let's see if we can even get that working, because I don't think I have installed NumPy. Okay, so we have that. Then let's make a super simple thing to compress that just has like 80% of one thing and 20% of another. So NumPy has this choice function, and we can choose what the probabilities are. So let's, for example, choose A and B. And the size we want is, let's try 100. And let's just print this for now, see what happens. So you can see here we have a bunch of A's and B's. So this is basically how we're going to generate the tests. So once we have that, I think let's call this one simple. And we are just gonna write this thing joined with nothing to that file. And let's try to run that. And now we should have this file simple. It just has a bunch of A's and B's. Okay, so you can see this should be compressible by a lot. So we can make a couple of others. For example, let's say A, B, C, D. And this one is just gonna be, let's say, mostly A. And this does not sum to 100, so let's do something like this. And this is gonna be, what are we gonna call this? Let's call it simple 4, because it has 4. This one, what should we do here? Let's do A and B, but completely equal probabilities. This one we can call equal to, I don't know, not feeling very inventive today. And this one, let's make it somewhat complex. And what should the probabilities be? How about, how many do we even have? Let's actually make it so we have 10, so that's 5. Oh, I forgot a letter. That's embarrassing. So now we have 10. And let's make them, like, here's one that's a little bit more likely. Then there's a couple of unlikely ones. And maybe there's one more that's a bit likely. And this gives us 1, 2, 3, 4, 5. Then we just have 2 more like that. And this is gonna be this? All right, let's try to run it and it completed. So here we have something like that. Here we have something like that. Here we have something like that. And this one has 10 different things, so that's a bit more complex. And we can even, maybe it's interesting to take this with 10 and make it even longer, so like that. And I think there's another thing we can do, if I'm not mistaken. Yeah, this one. So we can use this to get random bytes. So totally random bytes. So how about we get a 1,000 random bytes, and this one we just call completely random. And if we open that up, you can see it's just totally random. There should be no correlation here. All right, so that's it for the tests, for now at least. Let's try to get started on the actual coding. So I think probably we'll want to print some stuff, so let's get that one going, and return 0. And maybe today we want to have some arguments here, and then if it's less than 2, we're gonna say we want the program, of course, and then we want actually file to why am I keep writing underscore. So we want this stuff. So let us set up this thing. There we go. And now I run it, so it complains. And actually, let's set up the run script so it uses a specific file. So we're going to use tests, and let me just let's take simple, and then let's run it. Okay, so that succeeded. So the first thing we need is a sorted list. So let's make a type for it, and let's call it item for now because I cannot really think of anything. So there will be a specific byte, so we call that the value, and then there will be a useIST, which is the count. How many times does this value occur in the file? But first, let's do something. Let's try to read this file. So I think we do something like this. We read it, and then we have to remember to close it because it's C. And then I think, so we need to figure out how many elements there are. And there is something like, we can go to the end and then we can tell. And it's a very, very common pattern. First you go to the end and then you say, what byte number am I at? And then you go back to the start. So let's try this thing and then just print what the file size is, and let's see what happens. So isn't that a thing, useIST? Why am I getting my languages confused? Ask me later. Or is it just called SciST? And that might be it. Okay. So this one has 100 bytes, which is what we created it to have, so that's great. And then once we have that, we can say, yeah, let's make a buffer with the contents, and then just loop through it, I suppose. and we fill the buffer, and then we can even print the contents here. And let's see if that works. Okay, so now we get all the contents, and actually maybe this is a bit redundant. So what we should do is have some kind of hash map. So I'm going to be using STB. So we can just get that one and go here. And that should get it. So now we have this STB thing. So let's go ahead and include that, because then we would like to say we kind of need something like this, but it kind of expects a key value pair. So we're gonna have a key and we're gonna have a value. So we kind of do the counting in the hash map. So let me get here where the interface is described. Sorry about that. So this is how you make an empty hash map. So let's just call it hash map. And then here we need to see somehow, do we have this already? How do we check? Returns the index if in the hash map if it has the key, or -1 if the key is not present. So that's probably what we want. And let's go ahead and do that. So, okay. So do we have it? So let's get I, and we will use the hash map, and let's first read the char, current byte, let's say. We do that. And if we don't have it, then we're going to put it in with a count of 1. Otherwise, we're gonna return the current value. So size t current value is this, and then we're gonna put in the new value like that. And then we should be able to get rid of this buffer. We don't really need that. And then we can say for less than, and then it's called HM length. And then we can just print like this, I'm pretty sure. You just index the hash map by an index, and that should work. So let's go ahead and look. So we see 80 of A and 20 of B, exactly as we asked for. So how about we go here and we just list what's in test, and then we can comment that out. So we have this as a reference. And let's try with the random. And you can see it's all sorts of stuff and there's no real structure to it. That makes sense. And we can even try the Python file for fun. Okay. It's pretty interesting to see how compressible that is. How about this one? Should be 50-50. It's more or less 50-50. And let's go back to using this. All right. So that was an easy way we can get the count. This one we probably don't need anymore. And let's call this count. And then let's abstract this stuff into a function, which will say count bytes. Why not? And we'll take a file name, and we will do all of this. Put it in there. Here we just open the file name, and at the end we return the hash map. And we're going to say, here's the hash map, count the bytes, and this stuff actually should not have been here. Let's check that that still works. It still works. Okay. So now we have the counts. What are we going to do with them? Well, actually, we kind of need, or we would like a priority queue. We would like a priority queue. So what is a priority queue? It should be a list of things. So let's make it a list of counts, and it can have a size and capacity as well. And the key thing is that when you insert things, it's inserted using the priority, and the priority will be the lower the count, the higher the priority. Right, so we can do something simple where we just loop over the list and find out where the new item belongs, and then put it in there, and move everything up and then put it in there. And I think we're going to kind of say that the front of the queue is at the end of this array. So it's kind of easy to take elements off the array. I think that is a good thing. So let's say insert, let's call it pq insert, and we'll want the queue, and we'll want an item. And then basically we want to say for I equals pq size minus 1, I greater than or equal to 0, minus I. And then if the item, and we called it value up here, if the value is lower than the current value, then it has to be inserted in front of that. And so we basically first move everything above I one step up, then insert the item at I. And then we kind of continue, and once we have done this, I guess we can just return. If we get all the way here and we haven't inserted it yet, so we haven't returned, then it has to be at the very end of the list. All right, so we want to say for j equals, well, wait a second. Yeah, so I plus 1, j less than the size, plus. Then we're going to take the previous thing and move it 1 up. All right. And then the data at I can be the item. But there's a problem here because what did I just do? Sorry, the item at here. Okay. And then we'll have a similar loop here, except we start at 0. And then this will be inserted at 0. So I think that should do it. There is one issue, and we need to check the size first. So if the size plus 1 is greater than or equal to, well, greater than the capacity, then we need to reallocate everything to get some more space. And I think that should do it. So let's make a priority queue, and that will do it. So first let's also check here if the capacity is equal to 0, then we'll say that the initial capacity is actually 8. Otherwise we just double it. So let's see that it compiles. It compiles still, and then let's insert all of these things. And then we can actually go ahead and loop over the priority queue and do this stuff. So that did not work because we need to remember to increment the size. And that only gave 1 because we didn't increment it up here. So let's increment it before we do anything. No, that's wrong. We need to increment it here and here. Just okay. So now you can see. Let's do a. Well, now it's D. And the I as well. So this one has the lowest priority, which makes sense. This one has a higher priority. We can test some more complicated cases just to stress test the priority queue. And you can already see that it has broken somehow. Has broken. How did it break? Because these counts are definitely not correct. So I'm just moving that data. That should be fine. There's nothing weird going on in there. And we could also just print that stuff, and then let's also print you know, some stuff like that. Okay, so also the counts are actually messed up, but even so, the ordering, maybe it's this formatting. Okay, that's shouldn't be it. Let's do a little bit of debugging. So first I think I need to just run it to compile it, and then we can actually do this stuff. And where do we want to break? want to break on count bytes. And why does it say no debugging symbols found? That's a bit weird. Because you don't put it there, you put it when you compile. Alright. Then I will break here and let's run it. Let's get, and that, of course, that didn't work, so we need to do this, and then we need to run it, but with the input tests, and we use test 10 like that. And of course we need to also remember to do this, and then we can run it, and now finally we are here. And let's display the current character, which is D, whatever. Okay, it's probably not too interesting. Let's make another breakpoint at line 31 and then continue. And then we can try to print the hash map, and maybe, is it like that? Yeah, then we have to do something like at 10. Okay. Right. So we get these values look fine. They look correct. How big was that file? We can do something like this. It's 1,000, so that makes sense. That makes a lot of sense. So let's try to print the hash map again to see that it hasn't been corrupted or something. All right. So what happens in here? So first, this should happen. Is it perhaps this reallocation that messes things up? But that should copy things. So. All right. Stick the hash map again. Nothing weird has happened there yet. I also see now that I was printing the priority queue there, which I shouldn't have done. But let's also print the priority queue data at 1. Sorry. So let's just like that. Okay, that makes a lot of sense. Priority queue data at priority queue.size. Can you do this? And then actually, can we just display that? Very nice. Okay, so now clearly it already went super wrong. And where even is P? Why is it inserting P? There should be no P. So what is hash map 1? If we print that, that makes a lot of sense. Okay, so what is I? I is 2. What is hash map 2? It's that. If we step in here, what is item? That is still the same. I think I see the problem now. It's this moving code that is wrong. So first of all, let me just get the PQ and write hash map instead, and then actually the data we can just get rid of. If we run that now, it looks noticeable. So this is wrong. It has to be like that. Okay, so if this is less than the value at I, then this thing has to be inserted at I plus 1. So this is correct. And now here we actually have to do this so that the item that is currently at I plus 1 is being moved 1 up. So I think it has to be like this, and let's try to run it. And now it looks more correct, doesn't it? So first of all, they're all in descending order. It has a bunch of times, which is wrong, but it's closer. It's closer to being correct. It's closer. So let's go here. So why does it have a million times? Is it because this thing doesn't work? It's just copying things. It's just, and also going above the size is not a good idea. So I think we want size minus 1, and then we go down to, yeah, that makes more sense. So we're kind of like, we have an array here, let's say A, B, C, D, and we want to move everything up 1. So what we're doing now is we're saying, okay, whatever is here, let's put B. This one is still B, right? So we put that one in, then we go here and say, okay, let's put whatever is behind us, which is B now. So I'm kind of copying B a bunch of times. If we instead start from basically here actually. So we start from the top and we look what's behind us. Okay, it's D, let's put in that. Then we go back, what's behind us, C, here, what's behind us, it's B. And then this one we will overwrite. All right, so that has to be greater than or equal to I plus 1, I think. It's minus minus. Because this way we start at size, which is correct. Even though it's like kind of off from what you normally, you'd say you start at size minus 1, but we do want this. Then you take the previous one and then you go down until j is equal to this value. And yeah, I think that's it. So this should be size minus 1. It should be greater than or equal to 0. And there we have it. So segmentation fault. So that's great. That is fantastic. So let's try the debugger again. And it's segfaulted somewhere there. Here. Okay, that's kind of weird, right? Because we had plus plus. Okay, yes, good. Okay, let's try to run it. So now it's working. Everything is in descending order, and we have 10 different symbols, and the numbers correspond to what they are up here. Great. So that's how we can get things into the queue. Now let's do something much easier, I think. Let's get something off the top of the queue. And basically, the thing we want is the top of the queue. So we need to say it like this. And then we just decrement the size, and that should be the item. So what we can do is we can say while PQ size is greater than 0, let's get an item by PQ pop, and then we'll print it, and then that's it. And actually, let's just do something like this, popping, and you can see we get them in increasing counts now. So I think now we have the tools we need to actually do the compression. Well, we need one more thing, because the way this compression algorithm works is you build a binary tree. So we need something, let's call it an H node for Huffman node. And these things, they need a left child and a right child, and we can also add a parent, and then they need a weight, and then they need an optional value. So we'll have something there, but it will only matter if you are a leaf node, which we'll see that later. So I actually want to just have a quick function here that is leaf, and it will take an H node, and it will check that the children are null. Okay, so before we start, let's make a little array. Let's have like capacity. Maybe it should be somehow related to the length of the number of characters, and but let's actually do it squared, just because. So here is the nodes, and I wonder how we are going to make them. Let's have also a length which is 0, so it's kind of like one of those dynamic arrays again. All right, so we actually want to say, while we still have something left to process, what are we going to do? And actually it has to be greater than 1, because we're going to get two things out, so A and B. And those are the items with the current lowest what do you call it? Occurrence, the current lowest count. Actually, now I'm thinking of it, this priority queue, it's not great that it's working on count. It should actually work on these nodes. Should work on the nodes. So let's try to fix that, and then we actually probably have to move this definition up here. And then we don't want the value, it's the weight. Let's call this thing the byte value. This is the same, this is the same, this is the same, that's the same. Okay, so but now when we insert things, we actually want to make a node and set it up like this. And then when we insert here, we insert node, and we could still print the hash map, but let's not. Let's do this one again, 0, and then we can say, okay, it's actually a hash, it's actually a node. Let's print that stuff, and then this should work. So it did not work. 87. This should be a node, and capital N. Go here, and these should be H nodes. Invalid next size. Okay. Okay. And size of count is not interesting. It's not what we want. We want the size of each node. All right. So now we can still pop them in ascending order. So that's great. Let's get rid of that for now. Right. So we actually want to insert the nodes we currently have into Okay, I think for now we're not going to use the parent pointer, but that is fine. So let's insert all of those, and then we can just check that it kind of worked. And it is, well, this is not really going to work, is it? So I think maybe this has to be like some pointers, because we kind of need to know. Is that how you do it? I don't know. No, it's not. It's over here. I think we need the pointers. That should work, and this one will now give you a pointer. Fantastic. So now, before we insert into the priority queue, we need to know what the pointers are. So I'm actually going to use size instead. And then we can simply insert nodes of I, but actually need the pointer to it. And then let's see if it runs. It doesn't run because of this. Okay. So that's correct. Let's try to pop everything. And we'll print here. See that we, let's remove that one. See that we still get it in ascending order. All right, so now I think we finally have everything we need. So the way the algorithm works is you get the two rarest occurring things, and you make a new node out of them. So this node is, we can can make it 0, but then, okay, so the left one is this one, the right one is that. The weight is the summed weight. It doesn't have a value. We had the byte value, but the intermediate nodes, they are like combinations of other nodes, so they don't really have values. Now we want to insert that into this list of current nodes we have, and then we want to add it into the queue. So we insert it into the queue, and that is actually the whole algorithm basically. So let's try to run it. It runs correctly. So actually this has now created the code book. So we can actually go ahead and say, what is the root? And do that, and let's try to print it. So that should exactly be 1,000, because that kind of encapsulates all of the elements. We can go ahead and try with the symbol. So now it's 100, so that's correct. But then how do we find, how does this give us a compression? Let's say. So we can try to now create a code word table. So basically we're going to go traverse through this tree here, and every time we go left we'll add a 0 to the code word, and every time we go right we'll add a 1. Once we reach a leaf node, then we have the code word for that particular value that is at the leaf node. So let's make kind of like a temporary buffer, and we can even initialize it. And then we want to say, okay, how do we want to do this? How do we want to do this? Let's go ahead, let's do something a little bit silly, because I cannot really think. So while not is leaf, the current one, it's not a leaf, we are going to just say, also we need an index. The temporary index one is just a 0, and then we're going to go left, and then at the very end we will have a leaf, and then let's print, this is the code word, and we can also print the, let's print also the character, so that should be current value, byte value, what did I call it, byte value, right? Yes. So the code word for, now this one is a bit silly, because there's only two things in this file, so the code words are super simple. But now you can see, okay, A is consisting of 2 zeros, and I'm kind of not too sure how we're gonna do this. Maybe let's make a type. So we'll have a code word which is first of all, what is it encoding? And then we also need what is the actual code for that. So let's call it like this. And then we also need like a book, let's call it a code book, which is kind of a dynamic array for this thing. So we can, let's define DA append. If the size is equal to greater than the capacity, then we reallocate. And this one we can call items. So items, 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 and then we assign to here. And unfortunately, I kind of want to assume that A is a pointer instead. Let's do it like this. A is a pointer, and that is that. I also have some pointers floating around here, which is not so nice. So maybe we just make a buffer like this, and we'll say side length. All right. So now let's say codebook is a codebook, and create codebook, and it will take the root. This stuff we can remove. Let's copy that. And there we go. It's going to return a codebook. And the root is just a node. Okay. So let's create the codebook. And then we want to actually let's get the codebook by pointer here, and then we'll do this, and it will go ahead and modify that. And this is going to be just a node. Now that doesn't work either. That doesn't work either. Okay, let's revert this stuff. It's more simple to think of it this way. But what do we do now? How do we traverse this tree? Kind of want to do it recursively somehow, but can we avoid that? Yeah, so I think we need to somehow do something. So let's make two new code words. So code word left, code word right, and let's put those into the codebook. No, does that work? Yeah, I think it might. We could get it to work, but this is very, very strange. Let's just, honestly, let's try to do something else. Let's try to have, like, make something that just goes through everything and prints it out. So traverse. And this can be current. So it would be something like, okay, if this is a leaf, then we just print some stuff. Otherwise, we traverse left and we traverse right. And we can even have like a level And then how do we do that? I think we can say, well, I don't know how to do that. So let's say just print a space, get 2 spaces. Like that. Like that. So let's run that, and you can see we get this kind of thing. So it's a bit weird to me that we have this kind of thing. Maybe let's do this. So we print that, and then we can also print the current weight. And let's try to run that. And that did not work. Because we shouldn't modify this, I think. Also, why should it segfold? That's a bit weird. That is a bit weird. It's because we shouldn't do this thing in case we are a leaf. So that also looks weird because we kind of need this thing. And okay. So now you can a little bit better see the structure of the tree. A little bit. So here we have the root. Then if we go left, we get F, and we get another node that has a weight of 413. And then if we go left again, we get A, and if we go right, we get F. Then we have kind of a large right subtree. Okay. So that is kind of what we would like to do. Something like this. So let's get the code book. Now, when we reach a leaf, we want to make a new code word and fill some stuff into that. So what is the byte value? The byte value is the current byte value. Great. What is the code? What is the code? We don't know that. We have to keep track of that. We have to keep track of that. So it's essentially, maybe it's a bit silly to have it as a string of characters. Like it should just be a number. So like code, because it's just a it's just a binary number. So let's do it like this. I think this makes a lot of sense. All right, great. So what is the current code in the very beginning? It's 0. And what happens when we go left? Well, then we need to decide. So let's say if we go left, we add a 0. So we can do this by like this. We right shift by 1, and then we kind of add a 0. We don't really have to do anything, but we just have it there to be explicit. Definitely not because Copilot suggested. And here we add a 1. And Then we can do a diagnostic here, inserting code, and it will be this. We can do that for this byte. Let's go ahead and comment this stuff out. And now it doesn't work. Why doesn't it work? Because we need the code book. We didn't pass the code book here. We also didn't pass it over here. Code book. And I forgot a comma. So how do we print in binary? Alright, so I just stole something from Stack Overflow because I couldn't really be bothered with this right now. So now we can print the code words. So you can see here how they look. I think there is a problem with this. There is a problem. Because really these two should have a 0 in front. So I think it's not enough just to store the number. Let's actually store it as a sequence of bytes, and then we need the length. And the length we can get from the level, I think. Yes, I think that's correct, because every time we do a split, we increase it by 1, so that's correct. And now we have to do something here. So how are we gonna do that? Probably we can say from code length -1 this thing, right? And then we can print the code. Now it's just a string, and then actually let's go ahead and add a 0 to 100 byte, so we can actually use it as a string. And let's try to see if that works. Did not work. Okay, great. Because this, of course, is just going to give 0 bytes out of 0 bytes, something like that. Okay. Still there's a problem, because one of the features of this encoding, so I just reversed everything. I just somehow reversed it. So let's, why did I do that? Let's do it like this. It's less than code length. And it has to be plus plus. And still, that's wrong. Okay, finally got it to work. So now it is definitely working. So this type of code is called a prefix code, which has the property that no code word is a prefix of another code word. So there's no other code word that starts with 0, 0. There's no code word other code word that starts with 0, 1, and so on and so forth. So that makes it a bit easier to decode. And I had to loop through the array one way and insert the other way. That's what went wrong. So now that we have done all of this, we should have a code book that has some nice stuff, and then we can actually loop through the code book. No, we cannot, because here when we're inserting, we're not actually inserting, so that makes a lot of sense. So let's insert, and now we have them. Now we have them. So that's great. And now we should try to encode something like this. So let's have this thing, which takes a file name, and we'll do exactly that. So kind of reading things twice, but let's do that anyway. Let's read things, and now we can try to compress it. So let's make a new dynamic. We can call it writer. And it should have some data, which is going to be a buffer. It's going to be a size and capacity. Actually, this is going to have to be items. So let's make a writer here, and then we're going to loop over the contents. So maybe we have to do string length, and that's like a little bit too much stuff happening right there. So then we need to include string.h. Alright, so for now let's just kind of like print things out. I don't want to do this anymore. So now you can see we have some bunch of bytes, actually 100 bytes. No, wait, which file is this? We have some number of bytes. So now we need to encode it. So we can go ahead and get the code word for this. So we need to loop over the code book, and if the byte value is the current byte, then we have the code word, so we can print this. So there we have it. Now we need to write those into the stream as bits. So how are we going to do that? Maybe we don't think about that just yet. Let's also actually make this the code word. Like that, and then we can actually just do this. And then we're going to say for j equals 0, j less than the length, we're just going to put it into this writer. And then we can go ahead and see how it would look like. Yes, exactly. Oops, shouldn't have closed it. And what are we doing here? It should just be one long line, I feel like. but it is not. It is not. Are we accidentally writing a new line character? No. So let's try to assert that the code word of J is, yeah, that's pretty good. And then we need assert. And what happens when we append the append? So let's go ahead and try something. Do that, and it says there are 0 lines. Okay, so it just had something to do with how things were printed, but it is a single line. So I don't know why it's saying there's 0 lines, but it is what it is. Okay, but we actually have a really poor encoding here, because every bit is stored as a byte. So what we need to do is, first of all, maybe let's 0 pad it. So size t, padding needed, and that should be the length of the writer. Yeah, like that. So, and then we're gonna put a bunch of zeros, and then let's go ahead and check it out. Now it should have some zeros at the end. So now it's divisible by 8. Then we can go ahead and take 8 things at a time and put those into, let's make a new writer. And we can go ahead and say 0, I is less than writer.size. We are going to take things 8 at a time. We're going to be building up a byte like this. And yeah, that seems correct. So we're kind of storing it now in big endian, but that should be fine. So now we can go over writer 2 and print those things. So we run that, and let's have a look at this. Okay, so this file in principle is equivalent. Can I count the bytes of that? It's in principle equivalent to the first thing. But okay, the bytes, there's 395 bytes. And what did we run it on? We ran it on test 10. So let's go ahead and count the bytes in that one. And that of course has 1000 bytes. It's a bit, forgot about that. And we have a like compression ratio of 40. The question is though, can we actually decompress it? So to do that, we need to loop over the compressed and kind of expand it into the bit string again, and then look up in the code book by the code, code book. We have to loop over all the items, and when we find something that matches the, yeah, it's a bit, we would actually like the binary tree again when we do the decoding. But I think we'll do that another time because this video is already quite long and there's probably some cleanup we can do. So I will see you on the next one. Bye bye.